Welcome to The Drowsy Astronaut, where we take slow journeys through space, one careful detail at a time. And tonight we explore the galaxy we call home. This will be a long journey spread across nearly 2 hours, and you can listen straight through, drift in and out, or fall asleep whenever your body feels ready. There is no rush, no test, no need to remember every fact, because the Milky Way will still be here tomorrow, turning quietly around us. I would love to know where you are listening from tonight, whether you are under clear skies or city lights, in bed, at work, or somewhere in between. Drop a comment if you're comfortable sharing. It is always a quiet joy to see how many corners of Earth gather here together. As we drift forward, I will carry you across our galaxy, from our neighborhood outward to the edges, then inward to the center, and back home again. I will keep the language simple, the pace unhurried, and the science steady, so you can picture each idea before we move forward. So, let us begin, here on Earth, on a planet orbiting a middle-aged star, in a galaxy that contains hundreds of billions of others. The Milky Way is not just above us, it is all around us. We live inside it, the way a bird lives inside the air. Everything you see in the night sky with your eyes alone, every star, every constellation, belongs to this one galaxy, our local island in space. Let's start exploring this island slowly, so you can feel the structure we inhabit, watching how beautifully it unfolds in front of us. Our sun sits in a quiet region of the galaxy, about 26,000 light-years from the center, roughly halfway out toward the edge of the disk. A light-year is the distance light travels in 1 year, moving at 300,000 kilometers per second, and it equals about 9 trillion kilometers. So when we say the center is 26,000 light-years away, we mean the light leaving there tonight began its journey toward us 26,000 years ago. That distance is vast, but the galaxy is patient, and everything within it moves on timescales we can barely sense. We orbit the galactic center in a nearly circular path, completing one full loop every 230 million years, and our speed is about 828,000 kilometers per hour. You cannot feel that motion because Earth, the Sun, and all nearby stars move together like leaves floating on the same stream. The last time our Sun was in this part of its orbit, dinosaurs had not yet appeared, and the next time we return here, the continents will have moved again. Galactic years are long, and our place in the turning wheel stays steady through the ages. Our neighborhood is called the Orion Arm, or sometimes the Orion Spur, a smaller branch connecting two larger spiral arms. It stretches about 10,000 light-years long and 3,000 light-years wide, and contains the stars you recognize in constellations like Orion, Taurus, and Perseus. We sit inside a bubble of low-density space called the local bubble, carved out by ancient supernovae that swept gas away hundreds of thousands of years ago. That clearing gives us a relatively clear view in certain directions, though dust still blocks much of the galactic plane. If you picture the Milky Way as a flat disk seen from above, the spiral arms curve outward like water swirling slowly down a drain. The major arms are named Perseus, Sagittarius, Scutum Centaurus, and Norma, each one a river of stars and glowing gas stretching thousands of light-years. Between the arms lie quieter regions where star formation slows, and older stars drift through space in loose formations. Our Orion arm sits between Perseus and Sagittarius, a minor structure but dense enough to hold our Sun and millions of neighbours. From Earth, we see the Milky Way as a band of light stretching across the sky, faint in cities, brilliant in dark country skies. That band is the combined glow of billions of stars, too faint to see individually, their light merging into a pale river overhead. The densest part appears in the constellation Sagittarius, toward the galactic centre, where the stars pack together most tightly. Looking the other way toward Auriga and Perseus, we see the outer disk, thinner and fainter, stretching toward the edge. We see the galaxy edge on because we live inside the disk, the same way you see a plate as a thin line when you hold it level with your eyes. If we could rise far above the Milky Way and look down, we would see a beautiful spiral with glowing arms curving outward from a bright central bulge. But we are embedded in the plane, surrounded by stars and dust, so our view is limited to what lies along our line of sight. That edge-on perspective shapes everything we observe: the brightness, the shadows, the patterns, and the questions we ask about our home. The disk of the Milky Way is about 100,000 light-years across, but only about 1,000 light-years thick in most places. Imagine a dinner plate with its width 100 times greater than its height, and you have a sense of the proportions we inhabit. Our Sun bobs up and down through the disk as it orbits, crossing the midplane every 30 million years, spending roughly equal time above and below. Right now we sit slightly above the plane, which gives us a clear view southward toward the centre, though dust still dims the light. Dust grains in the disk are tiny, mostly carbon and silicates, smaller than particles of smoke, but they scatter and absorb starlight efficiently. When you look toward the galactic plane, you see dark lanes cutting through the Milky Way. Those are dust clouds blocking the stars behind them. In visible light, we can only see a few thousand light-years, before dust makes everything dark, but infrared and radio waves pass through more easily. So astronomers use different wavelengths to map the galaxy, each one revealing structures hidden from our eyes, piecing together a fuller picture. The concept of living inside the galaxy took centuries to understand, because the stars around us gave no obvious hint of a larger structure. Early astronomers saw the Milky Way as a cloudy band, and some guessed it was made of stars, but telescopes were needed to confirm the truth. In the 1800s, William Herschel tried to map the galaxy by counting stars in different directions, but he did not know how dust was hiding the full extent. It was not until the 1920s that astronomers realized the Milky Way was just one galaxy among countless others, and that the universe extended far beyond what we could easily see. Harlow Shapley studied globular clusters, dense balls of old stars, orbiting the galaxy, and he used them to estimate the size and center of the Milky Way. He found that the Sun was not at the center, as many had assumed, but far out in the disk, displaced by thousands of light-years. That discovery shifted our cosmic address, placing us in the suburbs rather than downtown, and it humbled our sense of importance. Edwin Hubble later proved that fuzzy spiral nebulae were separate galaxies, expanding the known universe enormously, and the Milky Way became one member of a vast population. Today we know the Milky Way is a barred spiral galaxy, meaning it has a central bar-shaped structure from which the spiral arms emerge and curve outward. The bar is about 27,000 light-years long, made of stars and gas, and it rotates as a somewhat rigid body, shaping the flow of material inward and outward. Bars are common in spiral galaxies, appearing in about 2/3 of them, and they help funnel gas toward the center, where it can fuel star formation or feed the central black hole. Our sun orbits outside the bar, so we see it end-on from our perspective, a subtle structure revealed through careful mapping of stellar motions. The spiral arms are not solid structures like the spokes of a wheel. They are density waves moving through the disk, regions where gas and stars bunch together temporarily. Stars drift in and out of these arms over millions of years, the way cars slow in traffic, then speed up again after passing through. When gas clouds enter an arm, they compress and heat, and that compression triggers new star formation, so the arms glow brighter with young blue stars. The pattern stays visible even as individual stars move on, a lasting shape built from temporary gatherings across the galactic plane. Imagine floating high above the Milky Way, looking down at the spiral. You would see the Perseus arm sweeping outward to one side, glowing with young star clusters. The Sagittarius arm would curve inward, closer to the center, and the Scutum Centaurus arm would stretch along the far side, each one marked by bright nebulae where new stars are being born. Our Orion arm would appear as a minor spur, a short branch between larger structures, but still bright enough to stand out against the darker gaps. The bar would cut across the center, a yellowish, elongated bulge, and beyond the spiral arms you would see the smooth halo fading into darkness. From that imaginary vantage point, the galaxy would look peaceful, almost frozen, but in reality everything is moving, stars orbiting, gas flowing, and the spiral pattern slowly turning. The entire disk completes one rotation in about 200 million years, though the spiral pattern itself rotates at a different speed, like a wave moving through water. The rotation is differential, meaning stars closer to the center orbit faster, and those farther out move slower, creating the conditions for spiral waves to form. If you watched for millions of years, you would see the arms shift slightly, stars drifting through them, and new clusters lighting up as old ones fade into the background. Now picture yourself back on Earth, standing under a dark sky, looking up at the Milky Way, and knowing that every star you see is part of this vast turning wheel. The faint band stretching overhead is the combined light of billions of distant suns, each one with its own orbit, its own history, and perhaps its own planets. You are seeing the galaxy from the inside, edge on, the way a person standing on a road sees it as a line, not as a map from above, but as a lived experience. That perspective is rare in astronomy, because we cannot step outside to photograph our own galaxy. We must piece it together from within, star by star. The brightest region you see is towards Sagittarius, where the disk thickens and the star density increases. That is the direction of the galactic center, hidden behind layers of dust and gas. If you follow the band westward through Aquila and Cygnus, you trace the path of the Milky Way across summer skies, passing through rich star fields and dark rifts. Northward through Cassiopeia and Perseus, the band continues, curving toward Auriga and eventually fading as we look toward the outer edge of the disk. Each section holds different treasures, star clusters, nebulae, and dark clouds, all visible through binoculars or small telescopes under dark skies. The stars you see with your naked eye are all relatively close, most within a few hundred light years, members of our local neighborhood drifting through the Orion arm. Sirius, the brightest star in our night sky, sits just 8.6 light years away. Vega is 25 light-years distant, and Betelgeuse lies roughly 500 light-years out. These distances feel vast, but they are tiny compared to the full extent of the galaxy. We are seeing only the nearest fraction of our stellar community. Beyond a few thousand light-years, individual stars become too faint, and they blend into the general glow of the Milky Way, contributing to the band we see overhead. When you look at the Milky Way, you are looking at the combined light of stars in the galactic disk, the flat plane where most of the galaxy's stars, gas and dust reside. Above and below the disk lies the halo, a spherical region containing old stars in globular clusters and a diffuse population of ancient suns moving on long elliptical orbits. The halo is much larger than the disk, extending perhaps 300,000 light-years out, but it contains far fewer stars, and most of its mass is dark matter, invisible but detectable through gravity. We will explore the halo in more detail later, but for now, picture it as a faint sphere surrounding the bright disk, a quiet realm of old stars and unseen mass. Our position in the galaxy is neither central nor peripheral, neither special nor random. We sit in a typical location for a star like the Sun, in a spiral arm, orbiting at a steady pace. The fact that we live in a relatively calm neighborhood, without nearby supergiant stars or recent supernova explosions, may have allowed life on Earth to develop without catastrophic interruptions. Some regions of the galaxy are far more violent, with dense star clusters, massive stars exploding frequently, and intense radiation flooding the surrounding space. Other regions are quieter, with fewer stars and less activity, but our Orion arm strikes a balance, active enough to be interesting, calm enough to be stable. The Sun's orbit around the galaxy is not perfectly circular. It wobbles slightly up and down through the disk, crossing the midplane every 30 million years or so. Right now we sit about 50 light-years above the plane, moving upward at a gentle pace, and in another 15 million years we will reach our maximum height before falling back down. This vertical motion is common for stars in the disk, driven by gravitational interactions with gas clouds, spiral arms, and other stars, creating a rhythm that repeats over galactic time. The crossing of the plane has been linked, somewhat controversially, to cycles of comet impacts and mass extinctions on Earth, though the evidence remains debated among scientists. As we continue our slow orbit, the stars around us shift and change, some moving faster, some slower, all following their own paths through the galaxy. Over millions of years, the familiar constellations will distort. The shapes we recognize tonight will stretch and rearrange as individual stars drift to new positions. Orion will not always look like a hunter, and the Big Dipper will eventually lose its shape, but the overall structure of the galaxy will persist, the disk, the arms, and the center holding steady. Stars are born, stars die, and the galaxy recycles, their material into new generations, a cycle that has repeated for billions of years and will continue for billions more. Our Sun formed about 4.6 billion years ago, from a cloud of gas and dust enriched by previous generations of stars, and it has completed roughly 20 orbits around the galaxy since then. Each orbit is called a galactic year, and the Sun has lived through 20, witnessing the slow evolution of the Milky Way, though no one was here to record the journey until very recently. In that time, the galaxy has changed. Stars have formed and died. Spiral arms have shifted slightly, and smaller galaxies have been pulled in and consumed by the Milky Way's gravity. Yet the overall structure remains recognizable. A barred spiral with a central bulge, a flat disk, and a surrounding halo, the architecture of our cosmic home. The Milky Way is part of a larger structure called the Local Group, a collection of more than 50 galaxies bound together by gravity, and we will explore that community in detail later. For now, it is enough to know that we are not alone. The Andromeda galaxy, our nearest large neighbor, sits about 2.5 million light-years away, and dozens of smaller galaxies orbit around us and Andromeda. The Local Group itself is part of the Virgo supercluster, which contains thousands of galaxies, and the Virgo supercluster is part of an even larger structure called Laniakea, a vast cosmic web. But tonight we stay close to home, focusing on the Milky Way itself, the galaxy we inhabit, the structure we can see from within, and the place where our story began. Imagine again that you are floating in space, far from any planet, drifting through the disk of the Milky Way, surrounded by stars in every direction. Some stars are nearby, bright and clear, their colors visible, blue, white, yellow, orange, and red, each one revealing its age and temperature. Other stars are distant, faint points of light blending together, their individual identities lost in the crowd, contributing to the general glow of the galaxy. Gas and dust float between the stars, glowing faintly in some places, dark and opaque in others, sculpted by stellar winds and gravity into clouds, filaments, and sheets. You would see nebulae, vast clouds of gas lit up by nearby stars, some glowing red with hydrogen, others blue with scattered starlight, and still others dark, blocking the light behind them. Star clusters would dot the sky, tight groups of hundreds or thousands of stars, all born together from the same cloud, moving through the galaxy as families. Occasionally, a supernova would flare, a star exploding with the brightness of 1 billion suns, visible across the galaxy, and leaving behind a glowing shell of debris that fades over thousands of years. And always, in the background, the steady glow of countless stars, each one a sun, each one perhaps hosting planets, each one a potential home for life, or simply a beacon of light in the dark. This is the Milky Way, not as a picture in a book, but as a lived environment, a place where matter organizes into stars and planets, where light travels for thousands of years, and where gravity holds everything together in a slow, majestic dance. We are part of that dance, moving with the sun through the disk, orbiting the center, bobbing up and down and drifting slowly toward new regions of the galaxy over timescales far longer than human history. Our perspective is unique. We are conscious observers embedded in the structure we study. And every discovery about the Milky Way is also a discovery about our own origin, our place, and our future. So as we continue this journey, remember that you are not separate from the galaxy. You are made of its material, shaped by its history, and carried along by its motion through space and time. The Milky Way is a barred spiral galaxy, but understanding what that means requires us to build the picture piece by piece, starting with the disk we inhabit. The disk is where most of the galaxy's stars live, along with vast clouds of gas and dust, and it is the most active region where new stars form and old stars quietly fade. If you could shrink the Milky Way down to the size of a coin, the disk would be as thin as a sheet of paper, flat and circular, with a slight bulge in the middle. That thinness is important because it means stars and gas are confined to a narrow layer, and that confinement creates the band of light we see across our sky. The disk rotates, all the stars and gas moving in roughly the same direction, orbiting the center, though not like a solid wheel, Each part moves at its own speed. Stars closer to the center orbit faster. Stars farther out move slower. And this differential rotation creates the conditions for spiral arms to form and persist over billions of years. The Sun takes about 230 million years to complete one orbit, traveling at 828,000 kilometers per hour, though we never feel the motion because everything around us moves together. That orbital speed is fast enough to cross the entire diameter of Earth in less than 20 seconds, yet from our perspective, the stars appear almost motionless. Rotation keeps the disk flat, the way spinning pizza dough flattens into a circle. Centrifugal force and gravity balance each other, creating a stable structure that resists collapsing inward or flying apart. Without rotation, the galaxy would collapse into a dense sphere, pulled together by its own gravity, but the spinning motion spreads the material out into a thin disk. Galaxies that have lost their rotation, often through collisions or mergers, tend to be elliptical, round or oval-shaped, with stars moving in random directions rather than orderly orbits. The Milky Way's disk tells us it has had a relatively peaceful history, with enough time for rotation to organize the stars and gas into orderly motion. The thickness of the disk varies depending on what you measure. The young stars, gas and dust, are confined to a thin layer about 1,000 light-years thick, while older stars spread out into a thicker layer. Young stars stay close to the plane because they form from gas clouds, and those clouds are also confined to the plane, flattened by rotation and collisions with other clouds. Older stars have had time to be jostled by gravitational interactions with other stars, gas clouds and spiral arms, gradually gaining random motions that carry them above and below the plane. So the disk has a layered structure, a thin young disk and a thicker old disk, both rotating together but with different vertical distributions. Our Sun belongs to the thin disk moving in a nearly circular orbit and bobbing up and down with a period of about 60 million years, crossing the midplane twice per cycle. Right now, we sit slightly above the midplane, about 50 light-years up, and we are moving upward, heading toward our maximum height before falling back down. This vertical motion is driven by gravity, the combined pull of all the stars and gas in the disk. Acts like a spring, pulling stars back toward the midplane whenever they wander too far above or below. The motion is slow and gentle, nothing that would affect life on Earth, but it is a reminder that nothing in the galaxy is truly stationary. Everything moves in response to gravity. The spiral arms add complexity to the disk. They are regions where stars and gas are more dense, but they are not permanent structures. They are waves moving through the disk at a different speed than the stars themselves. Think of spiral arms as traffic jams on a highway. Cars slow down when they enter the jam, then speed up again when they leave. But the jam itself moves at a different speed than the cars. Stars and gas clouds slow down slightly when they enter a spiral arm. The increased density creates gravitational drag, and that slowing allows gas clouds to compress, triggering star formation. The newly formed stars are hot and blue, and they light up the spiral arm, making it visible. But those stars are short-lived, dying before they have a chance to leave the arm. So, the spiral arms glow bright with young blue stars, while the regions between the arms are dimmer, populated by older yellow and red stars that have had time to drift away. This is why spiral galaxies have such clear patterns. The arms are outlined by young stars, and the gaps are filled with older stars, creating a beautiful contrast. The Milky Way has several major spiral arms: the Perseus arm, the Sagittarius arm, the Scutum Centaurus arm, and the Norma arm, each one winding outward from the central bar. Our Orion arm is a minor structure, sometimes called a spur, because it is shorter and less prominent than the major arms, but it is still home to millions of stars, including our Sun. The spacing between spiral arms is not uniform. Some regions of the disk have closely packed arms, while others have wider gaps, and the pattern shifts slightly over time. Computer simulations show that spiral arms can form, dissolve, and reform, driven by gravitational instabilities in the disk, interactions with satellite galaxies, and the influence of the central bar. The arms we see today may not have existed a billion years ago, and they may look different a billion years from now, though the disk itself will persist, rotating steadily through deep time. So the spiral pattern is temporary, a fleeting structure, but the disk is permanent, the fundamental component of the galaxy that has existed for billions of years. The bar at the center of the Milky Way is another key feature, about 27,000 light-years long, made of stars moving in elongated orbits that maintain the bar's shape. Bars form in many spiral galaxies, perhaps 2/3 of them, and they play an important role in moving gas inward toward the center, where it can fuel star formation or feed the central black hole. The bar rotates as a somewhat rigid structure, faster than the stars at the outer edge of the bar, but slower than stars closer to the center, creating a complex pattern of motion. Our Sun orbits outside the bar, so we see it end on, a subtle structure that was difficult to detect until astronomers mapped the motions and positions of millions of stars. The bar's influence extends beyond its physical boundaries. Its gravity shapes the orbits of stars and gas throughout the inner galaxy, creating resonances that affect the spiral arms. Some stars near the bar get trapped in orbits that reinforce the bar's shape, while others are scattered into more random orbits, contributing to the central bulge. Gas clouds that enter the bar's gravitational field get funneled inward, compressed and heated, and some of that gas eventually reaches the very center of the galaxy, where it may fall into the supermassive black hole. The bar is not static, it evolves over time, growing stronger or weaker, rotating faster or slower, responding to the overall distribution of matter in the galaxy. Looking at the Milky Way from Earth, we cannot see the full structure because we are inside it, like trying to map a city while standing in the middle of a street. We see the disk edge on, a band of light stretching across the sky, and we must use indirect methods to infer the shape and structure we inhabit. Radio telescopes have been essential for mapping the galaxy because radio waves pass through dust that blocks visible light, allowing us to see gas clouds and star-forming regions hidden from optical telescopes. Infrared telescopes also help because dust glows in the infrared, and stars shine through the dust more easily at longer wavelengths, revealing the structure of the inner galaxy. Astronomers map the galaxy by measuring the positions and motions of stars, using parallax for nearby stars and other methods for more distant ones, building a three-dimensional picture of the disk. The Gaia spacecraft has measured the positions and motions of more than 1 billion stars, the most detailed map of the Milky Way ever created, revealing structures we had only guessed at before. From that data, astronomers have refined the shape of the spiral arms, the length and orientation of the central bar, and the distribution of stars above and below the plane. The picture is still incomplete because dust and distance limit what we can see. But every new survey adds more detail, bringing us closer to understanding the full structure of our galaxy. The disk is not perfectly smooth. It has wrinkles and warps, bends that twist the plane of the disk into a gentle S shape near the outer edges. These warps are thought to be caused by gravitational interactions with satellite galaxies like the Magellanic Clouds, which tug on the Milky Way's outer disk and pull it out of alignment. The Milky Way is not alone. It is surrounded by smaller galaxies, and their gravity affects the shape and motion of the disk, creating ripples and waves that propagate through the stars and gas. Computer simulations show that even a small satellite galaxy passing near the Milky Way can create a warp that lasts for hundreds of millions of years, slowly fading as the disk relaxes back toward flatness. The disk also has a flare, meaning it gets thicker toward the outer edges. The density of stars and gas decreases, and the vertical distribution spreads out, like the edge of a vinyl record. This flare is common in spiral galaxies, and it may be related to the decrease in gravitational pull at larger distances, allowing stars and gas to wander farther from the midplane. The outer disk is also older, with fewer young stars and less active star formation, because the gas density is lower and the spiral arms are weaker, reducing the compression needed to trigger new stars. So the disk is not uniform. It changes with distance from the center, becoming thinner, sparser, and older as you move outward until it eventually fades into the halo. The edge of the disk is not sharply defined. There is no clear boundary where the disk ends and the halo begins. Instead, the density gradually decreases until the disk blends into the surrounding space. Astronomers estimate the disk extends to about 80 or 90,000 light-years. From the center, though faint stars and gas can be found even farther out, scattered through the halo. Beyond the disk lies the halo, a roughly spherical region, containing globular clusters, old stars, and vast amounts of dark matter, which we will explore in more detail later. For now, picture the disk as the bright, active heart of the galaxy, where most of the light and activity occur, surrounded by the quiet, ancient halo. When you look at the Milky Way on a dark night, you are seeing the disk from inside, edge on, the combined light of billions of stars too faint to see individually. The bright patches are regions of active star formation, where young stars light up gas clouds, and the dark patches are dust clouds blocking the light behind them. The overall structure is beautiful, a river of light flowing across the sky, but it is also incomplete, because we can only see part of the galaxy from our vantage point inside the disk. To understand the full shape, we must use other wavelengths, other techniques, and other perspectives, piecing together a picture of the galaxy we call home. The center of the Milky Way is hidden from our eyes, buried behind thick clouds of dust and gas that block visible light. But it is there, a dense region of stars, gas, and a supermassive black hole. That black hole is called Sagittarius A, pronounced Sagittarius A star, and it holds about 4 million times the mass of the Sun, packed into a region smaller than the orbit of Mercury. We cannot see the black hole itself because black holes do not emit light, but we can see its effects on the surrounding stars and gas, and those effects confirm its presence and measure its mass. Astronomers have tracked stars orbiting Sagittarius A, watching them whip around the black hole at incredible speeds, some completing orbits in just 16 years. One star, called S2, comes as close as 17 light-hours from the black hole, traveling at nearly 3% the speed of light at its closest approach, and its orbit provides a precise test of Einstein's general relativity. The orbit matches the predictions of general relativity, showing that space-time curves sharply near the black hole and that the black hole's gravity dominates the motion of everything nearby. Other stars orbit farther out, taking longer to complete their loops, but they all confirm the same result. There is a massive invisible object at the center, and it can only be a black hole. The mass of Sagittarius A is enormous, but its influence is local. It affects stars within a few light years, but it does not control the motion of the entire galaxy. The supermassive black hole sits at the very center of the Milky Way, but it is quiet right now, not actively consuming large amounts of material, though it occasionally flares when gas falls inward. In the past, Sagittarius A may have been much more active, shining brightly as material spiraled inward, heating up and emitting intense radiation before crossing the event horizon and disappearing forever. Evidence of past activity comes from giant bubbles of hot gas, extending above and below the galactic plane, stretching for tens of thousands of light years, blown out by ancient outbursts from the black hole. These bubbles, called the Fermi bubbles, glow faintly in gamma rays, and they suggest that Sagittarius A was far more violent a few million years ago, before settling into its current dormant state. The region around Sagittarius A is crowded with stars, packed more densely than anywhere else in the galaxy, and the environment is harsh, with intense radiation and strong gravitational forces. Some stars orbit so close to the black hole that they experience extreme tidal forces stretched by the difference in gravity between their near and far sides, though none have been torn apart yet. In theory, a star could pass too close, crossing the tidal disruption radius, where the black hole's gravity overcomes the star's own gravity, pulling it apart into a stream of gas that spirals inward. Such events are rare, but they have been observed in other galaxies, and they produce bright flares of light as the gas heats up and glows before vanishing into the black hole. The stars near Sagittarius A are mostly old and red, but there are also some young blue stars, which is puzzling because star formation should be difficult in such a violent environment. Astronomers think these young stars may have formed farther out, then migrated inward, or they may have formed in a dense gas disk around the black hole, a process that is not fully understood. The presence of young stars so close to the black hole tells us that the center of the galaxy is more dynamic than we thought, with gas flowing inward, stars forming, and the black hole occasionally consuming material. Over time, the black hole will continue to grow, swallowing gas and stars that venture too close, though its growth is slow now, and it will take billions of years to double its mass. Surrounding the black hole is a dense concentration of stars called the nuclear star cluster, about 10 million solar masses worth of stars packed into a region only a few light years across. This cluster is so dense that if our sun were there, the nearest star would be only a few light weeks away, close enough that planetary orbits might be disrupted by passing stars. The nuclear cluster formed early in the galaxy's history, and it has been shaped by the black hole's gravity, with stars settling into orbits around the central mass, creating a dense spherical structure. Star collisions are rare even in the nuclear cluster, but they happen occasionally, producing exotic objects like blue stragglers, stars that appear younger than they should because they have merged with companions. Beyond the nuclear cluster lies the central bulge, a roughly spherical region about 10,000 light-years across, filled with old stars that formed early in the galaxy's history. The bulge is the oldest part of the Milky Way, containing stars that are 10 to 12 billion years old, and its shape is elongated by the central bar, creating a peanut-shaped or boxy structure. Stars in the bulge move on complex orbits, some looping around the bar, others moving up and down through the plane, and their motions create a thick, three-dimensional distribution of stars. The bulge glows yellow-orange because its stars are old, and it dominates the light from the inner galaxy, though dust prevents us from seeing it clearly in visible wavelengths. Infrared telescopes reveal the structure of the bulge more clearly because infrared light passes through dust, and the bulge contains some of the oldest stars in the galaxy, survivors from the earliest epochs of star formation. These stars are metal-poor, meaning they formed from gas that contained few elements heavier than hydrogen and helium, because not many generations of stars had lived and died yet to enrich the gas with metals. Metal-poor stars are fossils, preserving information about the early galaxy, and by studying their chemistry, astronomers can learn what conditions were like when the Milky Way was young. The bulge also contains younger stars and some active star formation, particularly near the central bar, where gas is compressed and heated by the bar's gravity, triggering new bursts of star birth. The gas in the central region is complex, with clouds moving at high speeds, some orbiting the center, others falling inward or being blown outward by stellar winds and supernova explosions. Radio telescopes detect clouds of molecular gas, the raw material for star formation, concentrated in the central few hundred light-years where densities are high enough to form new stars. Some gas is arranged in a ring around the center, about 500 light-years in radius, where the bar's gravity compresses the gas and triggers star formation in dense clusters. This ring is called the central molecular zone, and it contains millions of solar masses of gas, enough to form millions of new stars if conditions allow, though star formation is patchy and episodic. The environment near the galactic center is hostile to life as we know it, with intense radiation from hot stars, frequent supernova explosions, and the gravitational influence of the black hole creating a turbulent, chaotic region. Planets might exist around stars in the bulge or nuclear cluster, but they would experience higher levels of radiation, more frequent gravitational disturbances, and a sky filled with bright stars instead of the dark space we see from Earth. Life on such planets would face challenges we can only imagine, and if intelligent life exists there, their view of the galaxy would be very different from ours, with the black hole dominating their sky and the disk spread out around them. But we do not know if planets can even form in such a crowded environment, and if they do, whether they can remain stable long enough for life to arise, questions that remain open for future study. The distance to the galactic center is about 26,000 light-years, measured using a variety of techniques, including tracking the orbits of stars around Sagittarius A, observing variable stars called cepheids, and mapping the distribution of gas clouds. That distance is not perfectly known, with some uncertainty, but the current best estimate is 26,000 light-years, give or take a few hundred, and this measurement is critical for understanding the overall structure and scale of the galaxy. Light from the galactic center takes 26,000 years to reach us, so when we observe the center, we are seeing it as it was in the distant past, long before human civilization began. If something happened at the center today, a bright flare from the black hole, a supernova explosion, we would not see it for another 26,000 years, a reminder of the vast distances and timescales at play in the galaxy. The center is also the point around which everything in the galaxy orbits, the gravitational anchor that holds the Milky Way together. Though that gravity comes not just from the black hole, but from the combined mass of all the stars, gas, and dark matter in the inner galaxy. The black hole's mass is only a tiny fraction of the total. About 4 million solar masses compared to hundreds of billions for the entire galaxy. So the black hole does not control the motion of the whole system, only the stars very close to it. But the center is still special, a unique region where matter is concentrated, where the gravitational field is strongest, and where the history of the galaxy is written in the motions and chemistry of ancient stars. Understanding the center helps us understand how galaxies form and evolve, how supermassive black holes grow, and what role they play in shaping the galaxies that host them. Imagine traveling toward the galactic center, starting from our position in the Orion Arm, and moving inward through the spiral arms, passing star clusters, nebulae, and vast clouds of gas and dust. As you approach the Sagittarius Arm, the stars grow more numerous and the sky becomes brighter, filled with the light of millions of suns. Continuing inward through the Scutum Centaurus Arm, the star density increases further, and you begin to see the glow of the central bulge, a yellowish haze stretching across the sky. The dust thins out in some regions but remains thick in others, blocking your view, but infrared and radio light pass through, revealing the structure hidden from visible eyes. As you enter the bulge, the stars are so close together that the night sky would never be truly dark, with hundreds of stars bright enough to cast shadows. The Milky Way band would no longer be visible as a distinct feature, because you would be inside the densest part of the disk, surrounded by stars in all directions. Looking toward the center, you would see the nuclear star cluster, a dense ball of stars glowing brightly. And beyond it, if you could see in X-rays or radio waves, the region around Sagittarius A would glow with the radiation from hot gas and energetic particles. The black hole itself would be invisible, a dark spot in the center of the cluster, revealed only by the orbits of the stars around it and the occasional flare when gas falls inward. Closer still to the black hole, the stars move faster and faster, their orbits tight ellipses or wild loops, and the gravitational field becomes so strong that time itself begins to slow down relative to an observer far away. At the event horizon of the black hole, time stops completely, and nothing, not even light, can escape, making the black hole a one-way boundary in space-time. But you would never reach the event horizon alive, because the tidal forces would tear you apart long before you got there, stretching you into a thin stream of atoms falling toward the singularity at the center. This is the fate of all matter that crosses the event horizon. It disappears from the universe we can observe, joining whatever lies inside the black hole, a mystery that physics cannot yet fully explain. For now, we observe the center from a safe distance, watching the star's orbit, measuring the mass of the black hole and studying the gas and dust that surround it, building a picture of this extreme environment. The center is a laboratory for testing our understanding of gravity, of black holes, of star formation in hostile conditions, and of the role that supermassive black holes play in shaping galaxies. Every observation adds a piece to the puzzle. Every new technique reveals something hidden, and slowly we are learning how the center works, how it formed, and what it will become in the future. Sagittarius A is quiet now, but it will not stay quiet forever, and when it flares, when gas falls inward in large amounts, the center will light up, a beacon visible across the galaxy. The spiral arms of the Milky Way are among its most beautiful features, long, sweeping curves of stars and glowing gas that trace the structure of the disk. But they are not permanent, they are waves. Density waves, to be precise. Regions where stars and gas are temporarily concentrated, like traffic slowing on a highway, creating a pattern that moves through the disk at a different speed than the stars themselves. This concept took decades to understand, because astronomers first thought the spiral arms were solid structures, groups of stars moving together, but observations showed that stars drift in and out of the arms over time. The key insight came in the 1960s, when scientists realized that gravitational instabilities in the disk could create waves that organize stars and gas into spiral patterns, even though the stars themselves move independently. Picture a long line of cars on a highway, and imagine that at one point the cars slow down, bunch together, then speed up again as they pass through. The bunching creates a visible pattern, a traffic jam, that moves along the highway, but the individual cars are not stuck in the jam. They enter it, slow down, and leave it. Spiral arms work the same way. Stars and gas clouds move through the arms, slowing slightly as they enter because the increased density creates gravitational drag, then speeding up again as they leave the arm and continue their orbits. The arm itself moves at a different speed, slower than the stars in the outer disk, faster than the stars in the inner disk, creating a pattern that persists over millions of years. When a gas cloud enters a spiral arm, the increased density compresses the cloud, and that compression can trigger star formation, particularly if the cloud is already close to collapsing under its own gravity. The compression adds the final push, and the cloud fragments into smaller clumps, each one collapsing to form a star or a cluster of stars, lighting up the spiral arm with newborn suns. These new stars are hot and blue because massive stars burn their fuel quickly and shine brightly, and they are short-lived, dying in supernova explosions after only a few million years. By the time the stars have drifted out of the spiral arm, the massive blue stars have already died, leaving behind neutron stars or black holes, while the longer-lived yellow and red stars continue their orbits through the galaxy. This is why spiral arms glow so brightly. They are filled with young, blue stars that light up the gas around them, creating the beautiful nebula we see in images of spiral galaxies. The regions between the arms are dimmer, populated by older stars that have had time to drift away from their birthplaces, and the contrast between the bright arms and the dim gaps makes the spiral pattern visible. Our Sun formed in a spiral arm billions of years ago, probably in a dense cluster with thousands of other stars, but over time the cluster dispersed, and the Sun drifted away, moving through different arms as it orbited the galaxy. Right now we sit in the Orion arm, a minor spur, and in a few million years we will drift into the Perseus arm, passing through new regions of star formation before continuing our journey around the galaxy. The major spiral arms of the Milky Way are the Perseus arm, the Sagittarius arm, the Scutum Centaurus arm, and the Norma arm, each one extending thousands of light years and containing millions of stars. The Perseus arm lies outside our position, stretching from the bar outward toward the edge of the disk, and it is visible in the northern sky as a bright band of stars and nebulae. The Sagittarius arm lies inside our orbit, closer to the galactic center, and it passes through the constellation Sagittarius, where the Milky Way appears brightest in our sky. The Scutum Centaurus and Norma arms lie on the far side of the galaxy, mostly hidden from our view by the central bulge, but radio telescopes have mapped them by detecting the emission from gas clouds along the arms. The spacing between spiral arms is not uniform, and the arms themselves are not perfect spirals. They have branches, spurs, and gaps, creating a complex pattern that varies with distance from the center. Computer simulations show that spiral arms can be triggered by gravitational interactions with satellite galaxies or by instabilities in the rotating disk itself, and once formed, the arms can persist for hundreds of millions of years. But arms can also dissolve. If the conditions change, if the disk is disturbed by a collision, or if the density wave weakens, and new arms can form in different locations. The spiral pattern we see today is a snapshot, a moment in the galaxy's ongoing evolution. And if we could watch the Milky Way over billions of years, we would see the arms shift, reform, and change as the galaxy grows and ages. Star formation happens throughout the disk, but it is most active in the spiral arms, where gas clouds are compressed and conditions are right for gravitational collapse, and the rate of star formation varies from arm to arm. Some arms are more active than others, depending on the density of gas, the presence of massive stars that trigger new star formation through supernova shockwaves, and the gravitational influence of nearby structures. The Scutum Centaurus arm is one of the most active regions, with dense molecular clouds and bright star-forming complexes, while other arms are quieter, with less gas and fewer new stars being born. Star formation is not continuous. It happens in bursts, triggered by compression, by supernova shockwaves, or by collisions between gas clouds. And each burst produces a cluster of stars that gradually disperses over time. A typical star-forming region begins as a giant molecular cloud, a vast collection of cold gas and dust, mostly hydrogen, with a mass of tens of thousands or even millions of solar masses. These clouds are cold, only about 10 to 20 degrees above absolute zero, and dense by interstellar standards, though still far more tenuous than the best vacuum we can create on Earth. Gravity pulls the cloud together, but the cloud resists collapse because it has internal pressure from the random motions of gas molecules and because magnetic fields thread through the cloud, providing additional support. For the cloud to collapse and form stars, something must tip the balance, compressing the gas enough that gravity wins, and that something is often the passage through a spiral arm. As the cloud enters the spiral arm, the increased density from surrounding stars and gas compresses the cloud, and small dense regions within the cloud begin to collapse under their own gravity, forming cores. Each core grows denser and hotter as it collapses, and eventually the center becomes hot enough to ignite nuclear fusion, turning hydrogen into helium and releasing energy that stops the collapse. At that moment, a star is born, glowing with the light of nuclear fire, and the surrounding gas and dust form a disk around the star, from which planets may eventually form. The process takes millions of years from start to finish, and not all cores become stars. Some fail to collapse completely, while others merge with neighbors or are disrupted by nearby radiation. Massive stars form in the densest parts of molecular clouds, where the gas is compressed most strongly, and these stars are rare but incredibly bright, thousands of times more luminous than the sun. Their intense ultraviolet radiation ionizes the surrounding gas, creating glowing nebulae called HII regions, named after ionized hydrogen, and these nebulae are some of the most beautiful objects in the galaxy. The Orion Nebula is a nearby example, a star-forming region visible to the naked eye, where young massive stars light up the gas around them, and new stars are still forming deep within the cloud. These massive stars live fast and die young, burning their fuel in just a few million years, then exploding as supernovae, scattering heavy elements into space and triggering new rounds of star formation with their shockwaves. Lower mass stars like the Sun form in less dense regions, and they take longer to form, perhaps 10 million years from the initial collapse to the ignition of fusion, and they live much longer, billions of years. Most stars in the galaxy are low-mass red dwarfs, stars smaller and cooler than the Sun, and they are so long-lived that none of the red dwarfs formed in the early galaxy have yet reached the end of their lives. The Sun is a medium-mass star, neither the smallest nor the largest, and it formed about 4.6 billion years ago in a molecular cloud that has long since dispersed, leaving the Sun to orbit the galaxy alone. Our birth cluster, the group of stars that formed with the Sun, has scattered across the galaxy, and we have no way to identify our siblings, though they are out there somewhere, moving on their own paths through the disk. Star clusters are groups of stars that form together, and they come in two main types: open clusters and globular clusters, each with different properties and histories. Open clusters form in the disk from molecular clouds, and they contain dozens to thousands of stars, loosely bound by gravity and spread out over tens of light years. The Pleiades is a well-known open cluster, visible in the constellation Taurus, a group of young blue stars that formed about 100 million years ago and are still loosely associated, though they will eventually disperse. Open clusters are temporary structures, lasting only a few 100 million years before gravitational interactions with other stars and gas clouds pull the cluster apart, scattering its members across the disk. Globular clusters are very different. Ancient spherical collections of hundreds of thousands or even millions of stars, tightly packed into a region only tens of light years across, and they orbit in the halo outside the disk. These clusters formed early in the galaxy's history, more than 10 billion years ago, and their stars are metal poor, indicating they formed from gas that had not yet been enriched by many generations of supernovae. Globular clusters are fossils, preserving information about the early Milky Way, and by studying their stars, astronomers can learn about the conditions and chemistry of the galaxy when it was young. The Milky Way has about 150 known globular clusters, and they orbit the galaxy on long elliptical paths, sometimes plunging through the disk, other times arcing high above or below it. Star formation in the Milky Way continues today, at a rate of about 1 to 2 solar masses per year, meaning the galaxy creates enough new stars each year to equal the mass of the Sun, or perhaps twice that. This rate has declined over time because much of the gas has already been used up, converted into stars, or ejected from the galaxy by supernova explosions and stellar winds. Billions of years ago, the star formation rate was much higher. The galaxy was richer in gas, and massive stars formed more frequently, creating a brighter, more active environment. In the future, star formation will continue to decline, as the remaining gas is slowly consumed, and eventually the Milky Way will become a quiescent galaxy dominated by old stars with few new ones being born. But for now, the spiral arms remain active, new stars continue to form, and the disk glows with the light of young blue suns, hot nebulae, and the quiet glow of older stars drifting between the arms. Each star that forms adds to the galaxy's population, and each star that dies returns material to the interstellar medium, enriching the gas with heavy elements that will be incorporated into the next generation of stars and planets. This cycle of birth and death has continued for billions of years, and it will continue for billions more, shaping the galaxy and creating the chemical diversity that makes planets and life possible. The spiral arms are not just beautiful structures, They are the engines of creation, the places where gas becomes stars, where stars create elements, and where the galaxy renews itself across deep time. The Milky Way contains between 200 and 400 billion stars, a number so large it is difficult to comprehend, and each star is a sun, potentially with its own family of planets. If you tried to count them one per second, it would take thousands of years to finish. And even then, you would only be counting the stars, not the countless planets, moons, and smaller objects that orbit them. These stars are not identical. They come in a wide range of masses, temperatures, colors, and ages, and each star tells a story about when and where it formed and what its future holds. Understanding the stellar population means understanding the galaxy itself, because stars are the building blocks, the light sources, and the creators of heavy elements that make planets and life possible. Stars are classified by their temperature and color, from hot blue stars at the high end through white, yellow, and orange, down to cool red stars at the low end, and the classification system uses letters that seem random but have historical roots. The sequence is O, B, A, F, G, K, M, from hottest to coolest, and astronomers remember it with mnemonics, some more polite than others. But the sequence itself is based on the strength of spectral lines in starlight. O and B stars are the hottest and most massive, glowing blue-white, with surface temperatures above 10,000 degrees, and they are rare, short-lived, and incredibly luminous, visible from great distances. G stars, like our Sun, are middle of the road, yellow in color, with surface temperatures around 5,500 degrees, and they are common enough that billions exist in the galaxy. M stars are the coolest and least massive, glowing red, with surface temperatures below 3,500 degrees, and they are the most common type of star, making up about 70% of all stars in the galaxy. Red dwarfs, as M stars are often called, burn their fuel so slowly that they can live for trillions of years, far longer than the current age of the universe, and none have yet reached the end of their lives. This means every red dwarf that has ever formed is still shining today, and they will continue shining long after larger stars like the Sun have died, making them the ultimate survivors of the stellar population. Their longevity also means they are potential hosts for life, because planets orbiting red dwarfs have immense amounts of time for life to develop, though the close orbits required for warmth create challenges like tidal locking and stellar flares. Massive stars at the other end of the scale, O and B stars, live only a few million years before exhausting their fuel, and they die in spectacular supernova explosions that can outshine entire galaxies for a brief time. These stars are rare because they form less frequently, and because they die quickly, so at any given moment there are only a few thousand of them in the entire Milky Way scattered through the disk. When a massive star explodes, it scatters heavy elements into space, elements like carbon, oxygen, iron, and gold, all forged in the star's core or in the explosion itself, enriching the interstellar gas. Those elements eventually become part of new stars and planets, which is why the Sun and Earth contain heavy elements. We are made from the ashes of ancient stars that died billions of years ago. The Sun is a G-type star, about 4.6 billion years old, halfway through its expected lifespan of 10 billion years, and it is neither exceptionally large nor exceptionally small. It is often called an average star, though in truth most stars are smaller and cooler, so the Sun is actually above average in both mass and luminosity. In about 5 billion years, the Sun will exhaust the hydrogen in its core, and it will begin to swell into a red giant, growing so large that its outer layers will engulf Mercury, Venus, and possibly Earth. Eventually, the outer layers will drift away, leaving behind a white dwarf, a dense remnant about the size of Earth, but with half the Sun's mass, slowly cooling over trillions of years until it fades into darkness. White dwarfs are the end state for stars like the Sun, no longer producing energy through fusion, supported only by electron degeneracy pressure, a quantum mechanical effect that prevents the star from collapsing further. They glow from leftover heat, gradually fading over billions of years, and eventually they will become black dwarfs, cold, dark remnants that emit no light, though the universe is not yet old enough for any black dwarfs to exist. Neutron stars are the remnants of more massive stars, formed when a supernova explosion compresses the core into a ball of neutrons, about 20 kilometers across but with 1 to 2 solar masses, incredibly dense and exotic. A teaspoon of neutron star material would weigh billions of tons. And the surface gravity is so strong that the escape velocity is about half the speed of light, making neutron stars some of the most extreme objects in the universe. Some neutron stars spin rapidly, emitting beams of radiation from their magnetic poles. And if those beams sweep across Earth, we detect them as pulses, earning these objects the name pulsars. Pulsars are incredibly precise clocks, some spinning hundreds of times per second, and their pulses arrive with such regularity that they can be used for navigation, studying gravitational waves, and testing fundamental physics. The fastest pulsars are called millisecond pulsars, spinning at rates of hundreds of rotations per second, and they were spun up by accreting matter from a companion star, transferring angular momentum and accelerating the neutron star's rotation. Pulsars gradually slow down over time, losing energy through magnetic braking and gravitational wave emission, and eventually they will stop pulsing, becoming quiet neutron stars that are nearly impossible to detect. Black holes are the end state for the most massive stars, formed when a supernova explosion cannot halt the collapse, and the core keeps shrinking until it becomes a singularity, a point of infinite density surrounded by an event horizon. Stellar mass black holes range from about 3 to 10s of solar masses, and they are invisible unless they are accreting matter from a companion star, which heats up and glows brightly before crossing the event horizon. The Milky Way likely contains millions of stellar mass black holes, scattered throughout the disk, but only a few dozen have been detected, found through their gravitational effects on companion stars, or through gravitational wave signals when they merge. Merging black holes produce ripples in space-time, detectable by instruments like LIGO and Virgo, and these detections have opened a new way to study black holes, measuring their masses and spins with incredible precision. Binary stars are common in the galaxy, systems where two stars orbit each other bound by gravity, and they offer unique opportunities to study stellar masses because the orbital motion reveals how much each star weighs. Some binaries are wide, with the stars separated by hundreds or thousands of astronomical units, orbiting slowly over centuries, while others are close, with orbital periods of hours or days, and the stars nearly touching each other. Close binaries can interact, with one star stripping gas from the other, or the two stars merging to form a single more massive star. And these interactions produce exotic objects like blue stragglers, novae, and type Ia supernovae. Type Ia supernovae occur when a white dwarf accretes matter from a companion, eventually reaching a critical mass where carbon fusion ignites explosively, destroying the white dwarf and producing a supernova with a predictable peak brightness. These supernovae are used as standard candles because their peak brightness is consistent, allowing astronomers to measure distances to other galaxies, and they played a key role in discovering that the universe's expansion is accelerating. In the Milky Way, stellar populations are divided into two main groups: Population 1 stars, which are young, metal-rich and found in the disk, and Population 2 stars, which are old, metal-poor and found in the halo and bulge. Population 1 stars formed recently from gas enriched by previous generations of stars, and they contain about 2% heavy elements by mass, similar to the Sun. Population 2 stars formed early in the galaxy's history, from nearly pristine gas containing very few heavy elements, and their low metallicity tells us they were born when the galaxy was young and had not yet cycled much material through stars. The distinction between populations is not sharp. There is a continuum of ages and metallicities, but the broad pattern holds: younger stars in the disk, older stars in the halo, reflecting the galaxy's evolutionary history. The disk formed later, after the halo, as gas settled into a rotating plane, and star formation in the disk has continued to the present day, while the halo formed quickly and has been mostly quiet since. Globular clusters in the halo are dominated by Population 2 stars, red giants and red dwarfs with low metallicity, and by studying these clusters, astronomers can estimate the age of the galaxy, currently thought to be about 13 billion years old. The oldest stars in the Milky Way are nearly as old as the universe, formed just a few 100 million years after the Big Bang, and they are rare, metal-poor survivors that have witnessed almost the entire history of cosmic evolution. Variable stars are stars whose brightness changes over time, and they come in many types, some pulsating regularly, others erupting unpredictably, and each type provides information about stellar physics and distances. Cepheid variables are particularly important because their pulsation period is directly related to their luminosity, and by measuring the period, astronomers can calculate the star's intrinsic brightness and use it to determine distance. These stars were crucial in measuring the size of the Milky Way, and in discovering that spiral nebulae were actually distant galaxies, forever changing our understanding of the universe's scale. RR Lyrae variables are another important type, older stars found in globular clusters, and they also serve as distance indicators, helping astronomers map the structure of the halo and measure the galaxy's size. Imagine looking at the Milky Way and seeing every star as an individual, each one with its own color, its own age, its own story, some young and blue, others old and red, and countless in between. The diversity is staggering, from stars barely massive enough to sustain fusion to giants hundreds of times the Sun's mass, and from stars just forming today to stars that have been shining for nearly the entire age of the universe. Each star is a nuclear furnace, converting hydrogen to helium, releasing energy that lights up the galaxy, and in the process creating the heavier elements that make planets, life, and everything we see around us. The stellar population is constantly changing. Stars are born, stars die, and the galaxy evolves, slowly transforming as old stars fade and new ones take their place. When you look at the Milky Way, you are seeing light from stars at different distances, different ages, different stages of life, all blending together into the band we see across the sky. Some of those photons left their stars thousands of years ago. Others left millions of years ago. And they have been traveling through space ever since, finally reaching your eye tonight. The light carries information. about the star's temperature, its composition, its motion, and its distance. And by analyzing that light, astronomers can learn the life story of each star without ever leaving Earth. This is the power of astronomy, the ability to study objects we can never touch, using only the light they send across the vast emptiness of space. Beyond the disk lies the halo, a roughly spherical region extending perhaps 300,000 light-years from the center, though its boundaries are not sharply defined, and it fades gradually into intergalactic space. The halo is home to the galaxy's oldest stars, found in globular clusters and scattered as individual stars moving on long elliptical orbits, and it also contains most of the galaxy's dark matter, invisible but detectable through its gravitational effects. Unlike the disk, the halo does not rotate as a coherent structure. Its stars move in random directions, some orbiting clockwise, others counterclockwise, and many plunging through the disk on highly elliptical paths. This random motion tells us the halo formed differently than the disk, probably through the merger of smaller galaxies early in the Milky Way's history, before the disk had time to form and settle. Globular clusters are the most visible inhabitants of the halo, dense spherical collections of stars that orbit the galaxy like distant satellites, sometimes passing through the disk, other times arcing far above or below it. The Milky Way has about 150 known globular clusters, each containing hundreds of thousands to millions of stars, tightly packed into regions only tens of light-years across. These clusters are ancient, more than 10 billion years old, and their stars are metal poor, indicating they formed from gas that had not yet been enriched by many generations of supernovae. The ages of globular clusters provide a lower limit on the age of the galaxy, because the Milky Way must be at least as old as its oldest stars, and current estimates place the galaxy's age at about 13 billion years. Globular clusters are so tightly packed that their cores are crowded, with stars separated by only light weeks or light months, far closer than the light years that separate stars in the solar neighborhood. Stellar collisions are rare even in globular clusters, but they do happen occasionally, producing exotic objects like blue stragglers, stars that appear younger than they should, because they formed from the merger of two older stars. The clusters are held together by gravity, but they slowly lose stars over time through a process called evaporation, where stars gain enough speed through gravitational interactions to escape the cluster's gravitational pull. Over billions of years, globular clusters gradually shrink and fade, and eventually they will dissolve completely, their stars scattering through the halo, though this process takes longer than the current age of the universe. Between the globular clusters lie individual stars, scattered through the halo, moving on long elliptical orbits that carry them far from the disk and then back again over millions of years. These stars are also old and metal poor, similar to the stars in globular clusters, and some may have escaped from clusters, while others formed in the halo or in small dwarf galaxies that were later consumed by the Milky Way. The density of stars in the halo is extremely low, far lower than in the disk, and if you were standing on a planet orbiting a halo star, the night sky would be much darker, with fewer visible stars and no bright Milky Way band overhead. From the halo, the Milky Way would appear as a distant disk, a flattened spiral seen face-on or edge-on depending on your position, glowing faintly with the combined light of billions of stars too far away to see individually. High-velocity stars are another component of the halo. Stars moving faster than typical disk stars, and their orbits often take them on steep paths through the galaxy. plunging through the disk and then arcing back into the halo. Some high-velocity stars are old halo stars, moving on elliptical orbits that happen to pass through our neighborhood, while others are stars that were ejected from the disk by gravitational interactions with massive objects or supernova explosions. A few high-velocity stars are moving so fast they will eventually escape the galaxy entirely, becoming intergalactic wanderers, and these stars are called hypervelocity stars, traveling at speeds of hundreds or thousands of kilometers per second. Hypervelocity stars may have been ejected by the supermassive black hole at the galactic center, or by interactions in dense star clusters and by studying their trajectories. Astronomers can learn about the extreme events that launched them into space. Dark matter dominates the mass of the halo, making up about 80 to 90% of the total mass, and it forms a spherical distribution that extends far beyond the visible stars and gas. Dark matter does not emit, absorb, or reflect light, so we cannot see it directly, but we know it exists because of its gravitational effects, the way it bends light, influences the motions of stars, and shapes the structure of the galaxy. The rotation curve of the Milky Way provides strong evidence for dark matter, because stars in the outer disk orbit faster than they should if only the visible matter were present, indicating there is additional invisible mass holding them in their orbits. Without dark matter, the outer stars would fly off into space, unbound by the galaxy's gravity, but the dark matter's gravitational pull keeps them in stable orbits, maintaining the galaxy's structure over billions of years. The nature of dark matter remains one of the biggest mysteries in physics. Astronomers know it exists. They can measure its gravitational effects, but they do not know what it is made of or how it interacts with normal matter. Leading candidates include weakly interacting massive particles, or WIMPs, hypothetical particles that interact only through gravity and the weak nuclear force, and axions, lightweight particles that were proposed to solve a different problem in particle physics. Experiments around the world are searching for dark matter, using detectors deep underground to shield from cosmic rays, looking for the rare collisions between dark matter particles and normal atoms. But so far, no definitive detection has been made. Dark matter may also be detected indirectly by looking for the products of dark matter particles annihilating when they collide, producing gamma rays or other radiation that telescopes can observe. The halo is not smooth. It contains substructure, clumps and streams of stars that reveal the Milky Way's history of merging with smaller galaxies, and by mapping these structures, astronomers can reconstruct the galaxy's past. Stellar streams are long, thin trails of stars stretched out along the orbits of dwarf galaxies that were torn apart by the Milky Way's gravity, and they can be hundreds of thousands of light years long, wrapping around the galaxy multiple times. The Sagittarius Stream is one of the most prominent, a trail of stars from the Sagittarius Dwarf Galaxy, a small galaxy currently being consumed by the Milky Way, and its stars are spread out in a long arc that circles the entire galaxy. By studying the chemistry and motions of stars in the stream, astronomers can learn about the original dwarf galaxy, how massive it was when it was captured, and how much of it has already been incorporated into the Milky Way. Other streams have been discovered, each one marking the death of a small galaxy that wandered too close to the Milky Way, and together they tell a story of galactic cannibalism, where large galaxies grow by consuming their smaller neighbors. The Milky Way has likely consumed dozens of small galaxies over its history, and their stars now orbit as part of the halo, mixed with the original halo stars, but still distinguishable by their chemistry and motions. Future surveys will discover more streams, mapping the halo in greater detail and revealing the full extent of the Milky Way's merger history, a history written in the positions and motions of billions of stars. Each stream is a fossil, a remnant of a galaxy that once existed independently, and by studying them, we learn not just about the Milky Way, but about how all galaxies grow and evolve through cosmic time. The halo also contains a few dwarf galaxies that are still intact, orbiting the Milky Way but not yet torn apart, and these satellites are small galaxies, each containing millions to billions of stars, bound to the Milky Way by gravity. The largest and most famous are the Large and Small Magellanic Clouds, visible in the southern sky as fuzzy patches of light, and they orbit the Milky Way at a distance of about 160,000 and 200,000 light-years respectively. The Magellanic Clouds are irregular galaxies, lacking the spiral or elliptical structure of larger galaxies, and they are rich in gas and active star formation, producing bright nebulae and young star clusters visible with small telescopes. They are close enough that individual stars can be studied, and they have been used as laboratories for understanding stellar evolution, variable stars, and the structure of small galaxies. Other dwarf galaxies orbit much farther out, and they are much fainter, containing only a few million stars, and some are so faint they were only discovered in recent years through careful surveys of the halo. These ultra-faint dwarfs are dominated by dark matter, with only a tiny amount of visible stars, and they are some of the most dark matter-rich objects known, providing important clues about how dark matter behaves on small scales. The discovery of these dwarfs has raised questions, because computer simulations predict there should be thousands of small dark matter halos orbiting the Milky Way, but we only see a few dozen with stars, suggesting that most small halos never formed stars. This discrepancy is called the missing satellites problem, and it is still being debated, with possible explanations including that small halos were prevented from forming stars by reionization, or that our simulations overpredict the number of small halos. The halo is the galaxy's memory, preserving the history of its formation and growth through the stars and streams that orbit within it, and by studying the halo, we learn how the Milky Way assembled itself from smaller pieces. The halo stars are the oldest citizens of the galaxy, survivors from the early universe, and they carry information about the chemical composition of the gas from which they formed, which in turn tells us about the first generations of stars that enriched that gas. Some halo stars have almost no heavy elements, just traces of lithium, beryllium, and boron, and these extremely metal-poor stars formed from gas that was enriched by only one or two supernovae, making them precious relics of the earliest epochs of star formation. By studying these ancient stars, astronomers can test theories of the first stars, which were likely far more massive than stars forming today, and which played a crucial role in shaping the early universe. The halo extends far beyond the visible stars, and its dark matter distribution reaches out hundreds of thousands of light-years, merging gradually with the dark matter halos of other galaxies in the local group. At some point, the Milky Way's halo blends into the halo of Andromeda, our nearest large neighbor, and the two galaxies are already gravitationally bound, slowly moving toward each other on a collision course. But that collision is still billions of years away, and for now the halo remains the Milky Way's outer boundary. a vast spherical shell of old stars and dark matter that defines the edge of our galaxy. From a cosmic perspective, the halo is what makes the Milky Way, a massive object, because most of the galaxy's mass is dark matter in the halo, and the visible disk and bulge are just the bright center of a much larger structure. The Sun orbits the center of the Milky Way, moving at about 828,000 kilometers per hour, and it takes approximately 230 million years to complete one full orbit around the galaxy. This orbital period is called a galactic year, and the Sun has completed about 20 galactic years since it formed 4.6 billion years ago, meaning we have gone around the galaxy 20 times in our entire history. Each orbit carries us through different regions of the disk, passing through spiral arms, traversing quieter regions between arms, and encountering different populations of stars, gas clouds, and dust as we move along our path. Right now, we sit in the Orion Arm, but in a few tens of millions of years, we will drift into the Perseus Arm, and eventually we will pass through other arms as we continue our endless journey around the galaxy. Our orbit is not perfectly circular. It is slightly elliptical, with the Sun moving closer to the galactic center at some points and farther away at others, though the variation is small, only about 1,000 light-years in radius. The orbit also carries us up and down through the disk because the Sun bobs vertically as it moves, crossing the galactic midplane every 30 to 35 million years and spending roughly equal time above and below the plane. Right now, we sit about 50 light-years above the midplane, and we are moving upward, heading toward our maximum height of about 250 light-years before gravity pulls us back down toward the plane. This vertical motion is driven by the combined gravitational pull of all the stars and gas. In the disk, which acts like a spring, pulling stars back toward the mid-plane whenever they wander too far above or below. The crossing of the galactic plane has been linked, somewhat controversially, to cycles of comet impacts and mass extinctions on Earth, the idea being that passing through the plane increases gravitational disturbances that send comets from the outer solar system toward the inner planets. The evidence for this connection is mixed, and many scientists remain skeptical, but it is an interesting idea that connects the Milky Way's large-scale structure to events on Earth, showing how galactic motion can have local consequences. Whether or not the plane crossing affects life on Earth, it is a reminder that we are not isolated. We are part of the galaxy's dynamics, moving through different environments as the Sun orbits, and subject to the gravitational influences of the structures around us. The Sun's orbit is stable. It has been following roughly the same path for billions of years, and it will continue to do so for billions more, barring some unlikely close encounter with another star or a massive gas cloud. The speed of 828,000 kilometers per hour sounds fast, but it is actually close to the circular velocity for an object at our distance from the galactic center. The speed needed to balance gravity and maintain a stable orbit. If we were moving faster, we would spiral outward, drifting to larger radii over time, and if we were moving slower, we would spiral inward, gradually falling toward the center. Our nearly circular orbit suggests the Sun formed at roughly the same distance we are now, and that it has not been significantly disturbed by gravitational interactions, though small perturbations have occurred over billions of years. The circular velocity decreases with distance from the center, so stars in the inner disk orbit faster, completing their circuits in less time, while stars in the outer disk move slower and take longer to go around. This differential rotation is what allows spiral arms to form and persist, because different parts of the disk rotate at different speeds, creating shear that organizes stars and gas into the wave-like patterns we see as spiral structures. If the disk rotated like a solid body, with all stars moving at the same angular speed, spiral arms would quickly wind up and disappear. But the differential rotation allows the density waves to maintain their shape over hundreds of millions of years. The spiral pattern itself rotates at a different speed than the stars, the pattern speed, and stars move through the arms, entering from one side, slowing down slightly, then exiting the other side and continuing their orbits. This separation between the motion of stars and the motion of the pattern is crucial for understanding spiral arms, and it was one of the key insights that helped astronomers explain why spiral galaxies look the way they do. Our motion through the galaxy is not just an orbit around the center. We are also moving relative to the local standard of rest, the average velocity of stars in our neighborhood, and that motion is called the sun's peculiar velocity. The sun is moving toward a point in the sky near the constellation Hercules at about 20 kilometers per second, relative to nearby stars, carrying Earth and all the planets along with it. This motion is small compared to our orbital speed, but it means the Sun is not perfectly following the average motion of the disk. It has a slight deviation that reflects its history of gravitational interactions with other stars and gas clouds. Over time, the peculiar velocity changes as the Sun encounters other structures and its orbit is gently nudged. But these changes are gradual, taking millions of years to accumulate into significant shifts. The entire Milky Way is also moving, not orbiting anything, but falling toward the center of the local group, the collection of galaxies that includes the Milky Way, Andromeda, Triangulum, and dozens of smaller dwarf galaxies. The local group itself is moving toward the Virgo cluster, a large collection of galaxies about 50 million light-years away, and the Virgo cluster is part of an even larger structure called the Laniakea supercluster. So the Sun's motion is layered, orbiting the Milky Way moving toward Andromeda, the local group moving toward Virgo, and all of it carried along by the expansion of the universe, making our true motion through space incredibly complex. But from our perspective, none of this motion is felt. We move with Earth, Earth moves with the Sun, and the Sun moves with the galaxy, all of it smooth and seamless, like riding on a vast cosmic carousel that never stops turning. Imagine watching the Milky Way from outside, seeing the disk rotate, stars moving in their orbits, spiral arms turning slowly, and the Sun tracing its long path through the disk over hundreds of millions of years. You would see the galactic center glowing brightly, the bulge and bar shining with the light of billions of old stars, and the disk spreading outward, thinner and fainter toward the edges. The spiral arms would light up with young blue stars and glowing nebulae, while the regions between the arms would appear dimmer, filled with older yellow and red stars that have had time to drift away from their birthplaces. The halo would be faint, dotted with globular clusters, and scattered with old stars moving on long elliptical orbits, and beyond it, the dark matter halo extending far into space, invisible but shaping everything with its gravity. From that outside view, the Milky Way would look like countless other spiral galaxies, beautiful, dynamic, and peaceful. A structure built from billions of stars all moving together, bound by gravity and slowly evolving over cosmic time. But we do not have that outside view. We are inside, embedded in the disk, moving with the Sun. and our perspective is unique, seeing the galaxy from within, learning its structure piece by piece, star by star. That inside view makes our journey of discovery more difficult, but also more personal, because we are not just observing the galaxy, we are part of it, made from its material, shaped by its history, and carried along by its motion through space. Every fact we learn about the Milky Way is also a fact about ourselves, because we are citizens of this galaxy, and our story is woven into its story, inseparable and eternal. The Milky Way does not exist in isolation. It is surrounded by a family of smaller galaxies, bound to us by gravity, orbiting our galaxy or moving in complex paths through the local group. These satellite galaxies are mostly dwarf galaxies, much smaller than the Milky Way, containing millions to billions of stars compared to our hundreds of billions, and most of them are faint, difficult to detect without careful surveys. The most famous satellites are the Large and Small Magellanic Clouds, visible in the southern sky as fuzzy patches, and they are the two largest and brightest dwarf galaxies orbiting the Milky Way. The Large Magellanic Cloud, or LMC, lies about 160,000 light-years away, and it contains roughly 30 billion stars, making it a substantial galaxy in its own right, though still much smaller than the Milky Way. The LMC is an irregular galaxy, lacking the organized spiral or elliptical structure of larger galaxies, and it is rich in gas and dust, with active star formation producing bright nebulae and young star clusters. The Tarantula Nebula, located in the LMC, is one of the most active star-forming regions known, so bright that if it were as close as the Orion Nebula, it would cast shadows on Earth at night. The Small Magellanic Cloud, or SMC, lies about 200,000 light-years away, slightly farther than the LMC, and it contains roughly 7 billion stars, smaller and fainter than its larger companion. The SMC is also an irregular galaxy, and it is gravitationally bound to the LMC, the two galaxies orbiting each other as they both orbit the Milky Way, creating a complex three-body system. The Magellanic Clouds are visible only from the southern hemisphere, and they have been known since ancient times, named after the explorer Ferdinand Magellan, whose expedition noted them during the first circumnavigation of the globe. Modern telescopes have revealed that the clouds are not isolated. They are surrounded by streams of gas called the Magellanic Stream, a long trail of hydrogen gas stripped from the galaxies by the Milky Way's gravity and ram pressure as they move through the halo. The Magellanic Stream stretches for more than 600,000 light-years, wrapping around the Milky Way, and it provides fuel for future star formation in our galaxy, gradually falling inward and eventually mixing with the disk. The clouds are also approaching the Milky Way, and in a few billion years, they may collide with the disk, merging with the Milky Way and adding their stars to our galaxy, a process that has happened many times in the past. Other dwarf galaxies orbit the Milky Way at greater distances, and most of them are much fainter than the Magellanic Clouds, discovered only in recent years through deep surveys that revealed faint overdensities of stars in the halo. The Sagittarius dwarf galaxy is one of the closest satellites, about 70,000 light-years away, currently passing through the disk of the Milky Way, and it is being torn apart by tidal forces, leaving behind long streams of stars. The Sagittarius Stream wraps around the entire galaxy multiple times, and it is one of the most prominent features in the halo, a clear sign of ongoing galactic cannibalism as the Milky Way consumes its smaller neighbor. Other known satellites include the Fornax, Sculptor, and Carina dwarf galaxies. each one a small collection of stars orbiting the Milky Way, and each one a potential source of stars and dark matter for our galaxy's future growth. Ultra-faint dwarfs are the smallest and faintest satellites, containing only a few thousand to a few million stars, and they are so dark that they are barely brighter than a single bright star, making them extremely difficult to detect. These galaxies are dominated by dark matter, with only a tiny amount of visible stars, and they are among the most dark matter-rich objects known, providing important clues about how small galaxies form and survive. The discovery of ultra-faint dwarfs has been accelerated by surveys like the Sloan Digital Sky Survey, and more recently by the Dark Energy Survey and other projects, which have revealed dozens of new satellites in the past 2 decades. As surveys become more sensitive, astronomers expect to find even more ultra-faint dwarfs, potentially hundreds of them orbiting the Milky Way, though most will remain too faint to study in detail with current technology. The distribution of satellite galaxies around the Milky Way is not random. They tend to lie in a flattened structure called the plane of satellites, a disk-like arrangement that is difficult to explain, with standard models of galaxy formation. This plane is controversial, and some scientists argue it is a statistical fluke, while others believe it reveals something important about how satellites are accreted or about the nature of dark matter. Similar planes have been found around other galaxies, including Andromeda, suggesting it may be a common feature, though the explanation remains unclear and is an active area of research. The satellites also show a lack of very massive dwarfs, which is puzzling because simulations predict there should be more massive satellites than we observe, another aspect of the missing satellites problem. Tidal streams from disrupted dwarf galaxies are common in the halo, and they provide a fossil record of the Milky Way's merger history, each stream marking the death of a small galaxy that was torn apart by our gravity. By mapping these streams in detail, astronomers can reconstruct the orbits of the original galaxies, estimate their masses, and learn when they were accreted, building a timeline of the Milky Way's growth. The Gaia spacecraft has been instrumental in discovering new streams by measuring the positions and motions of billions of stars and revealing faint structures that were invisible in previous surveys. Future missions will continue this work, mapping the halo in even greater detail and uncovering the full history of the Milky Way's interactions with its satellite galaxies. The Milky Way's satellites are not the only neighbours. We also have sibling galaxies in the local group, galaxies that orbit the same centre of mass but are not directly bound to the Milky Way. Andromeda, also known as M31, is the nearest large spiral galaxy, about 2.5 million light-years away, and it is slightly larger than the Milky Way, containing perhaps 1 trillion stars. Andromeda is approaching us at about 110 kilometers per second, and in about 4 billion years, the two galaxies will collide, merging to form a single larger galaxy, probably an elliptical galaxy. This future collision is one of the most dramatic events in the Milky Way's future, and it will reshape both galaxies, scattering stars, triggering bursts of star formation, and eventually merging the two supermassive black holes at the centers. Andromeda has its own family of satellite galaxies, including M32 and M110, two dwarf elliptical galaxies visible in telescopes, and dozens of smaller dwarfs discovered in recent surveys. The total number of satellites around Andromeda is similar to the Milky Way, suggesting both galaxies have had similar histories, growing by accreting smaller galaxies over billions of years. The Triangulum galaxy, also known as M33, is the third largest member of the local group, about 3 million light-years away, and it is a smaller spiral galaxy containing perhaps 40 billion stars. Triangulum may be gravitationally bound to Andromeda, and it may eventually merge with Andromeda or the Milky Way, or it may survive as an independent galaxy, its fate still uncertain. The local group also contains dozens of smaller dwarf galaxies, some orbiting Andromeda, some orbiting the Milky Way, and some moving independently through the space between the larger galaxies. The total mass of the local group is dominated by dark matter, with the visible stars and gas making up only a small fraction, and the center of mass lies roughly between the Milky Way and Andromeda, the two most massive members. The local group is part of the Virgo supercluster, a larger structure containing thousands of galaxies, and the Virgo supercluster is part of an even larger structure called Laniakea, which contains about 100,000 galaxies. These nested structures show that the universe is organized on multiple scales, from individual galaxies to groups like the local group to clusters and superclusters, all connected by the cosmic web of dark matter that threads through space. But tonight, we stay focused on the local group, the small family of galaxies that includes our own and the satellites that orbit around us, each one a small world with its own history, its own stars, and its own story to tell. These neighbors are our closest companions in the cosmos, and studying them helps us understand not just the Milky Way, but all galaxies, because the processes that shape satellites are the same processes that build large galaxies like ours. The satellites are also laboratories for studying dark matter, because they are so dark matter dominated, and by measuring their masses and structures, astronomers can test theories of what dark matter is and how it behaves on small scales. In many ways, the satellites are as important as the Milky Way itself, because they reveal the building blocks from which large galaxies are made, and they show us what the early universe looked like when galaxies were first beginning to form. The local group is our galactic neighborhood, a collection of more than 50 galaxies bound together by gravity, spanning about 10 million light-years, though most of the galaxies are small dwarfs. The Milky Way and Andromeda are the two dominant members, each with its own family of satellites, and together they account for most of the visible mass in the group, though dark matter makes up the majority of the total mass. Triangulum is the third largest member, followed by a few smaller but still significant dwarfs, and then dozens of ultra-faint galaxies discovered in recent years through deep surveys. The local group is moving as a whole, falling toward the Virgo cluster under the influence of gravity, and eventually the local group will merge with other structures in the Virgo region, becoming part of a larger cosmic web. Andromeda dominates the local group along with the Milky Way, and the two galaxies are on a collision course, moving toward each other at about 110 kilometers per second, though the collision is still 4 billion years away. When the galaxies collide, their disks will pass through each other, stars will be scattered, and the gravitational interactions will trigger intense bursts of star formation, creating bright blue clusters and glowing nebulae throughout the merging system. Individual stars will rarely collide because the distances between them are so vast, but the galaxies as a whole will merge, their stars mixing together, and their supermassive black holes eventually spiraling inward to merge at the center. The merger will take billions of years to complete, with multiple passages as the galaxies swing around each other, losing energy through gravitational interactions until they finally settle into a single larger galaxy. The result will likely be an elliptical galaxy, lacking the spiral structure of the original galaxies, and it will be called Milkomeda or Milkdromeda, a blend of the two names, though no one will be around to see it happen. The Sun will survive the merger, though its orbit will be disrupted, and it may end up in a different region of the new galaxy, possibly in the halo rather than the disk, with a very different view of the sky. By the time the merger happens, the Sun will be nearing the end of its life, beginning to expand into a red giant, and Earth will be uninhabitable or destroyed, so the collision will not affect life on our planet unless life has spread to other star systems by then. But the merger is important for understanding galaxy evolution, because it is a preview of what happens when large galaxies collide, and it shows how elliptical galaxies form from the mergers of spirals. Elliptical galaxies are common in the universe, especially in dense galaxy clusters where collisions happen frequently, and they are typically older, redder, and less active than spiral galaxies, with little ongoing star formation. The Milky Way Andromeda merger will transform two spiral galaxies into an elliptical, and similar mergers have happened countless times throughout the universe, shaping the galaxy population we see today. Triangulum may also be involved in the merger, though its fate is less certain because its orbit relative to the Milky Way and Andromeda is not perfectly known, and it may merge with one of the larger galaxies or escape the interaction. If Triangulum merges, it will add its stars to the growing elliptical, and if it escapes, it will become a solitary galaxy wandering through intergalactic space, its companions gone. Computer simulations of the merger show a variety of possible outcomes, depending on the exact orbits, masses, and angular momenta of the galaxies, but all scenarios end with a single large elliptical galaxy dominating the local group. The simulations are beautiful, showing the galaxies spiraling together, their disks warping and stretching, stars being flung into long tidal tails, and finally the two cores merging into one, a cosmic dance that takes billions of years. Beyond the local group lies the Virgo cluster, about 50 million light-years away, a large collection of more than 2,000 galaxies, including giant ellipticals, spirals, and countless dwarf galaxies. The Virgo cluster is the nearest large galaxy cluster, and its gravity affects the local group, pulling us toward it at about 200 kilometers per second, though we will not reach it for tens of billions of years, if ever. The center of the Virgo cluster is dominated by M87, a giant elliptical galaxy with a supermassive black hole at its center, the first black hole ever imaged directly by the Event Horizon Telescope in 2019. M87's black hole is about 6.5 billion solar masses, far larger than Sagittarius A star, and it powers a jet of energetic particles that extends thousands of light-years into space. The Virgo cluster is part of the Virgo supercluster, a larger structure containing dozens of galaxy groups and clusters, spanning about 110 million light-years, and the local group lies on the outskirts of this supercluster. But even the Virgo supercluster is not the largest structure. It is part of an even larger structure called Laniakea, a supercluster of superclusters containing about 100,000 galaxies and spanning 520 million light-years. Laniakea is defined by the flow of galaxies toward a common center of mass, called the Great Attractor, a region of enhanced density that pulls surrounding galaxies inward, and the Milky Way is moving toward this attractor as part of the larger flow. Beyond Laniakea lie other superclusters, separated by vast voids containing few galaxies. And together, these structures form the cosmic web, the largest scale structure in the universe, shaped by dark matter and gravity over billions of years. The cosmic web is a network of filaments and voids, with galaxies concentrated along the filaments, clusters forming at the intersections, and vast empty regions called voids containing almost no galaxies. The web formed from tiny density variations in the early universe, amplified by gravity over billions of years, and it reflects the underlying distribution of dark matter, which dominates the large-scale structure of the cosmos. Galaxies form where the dark matter is densest, and they trace the web's structure, lighting up the filaments and clusters while leaving the voids dark, creating a pattern that looks like foam or a sponge when viewed on the largest scales. The Milky Way sits on a filament, moving through the web as part of the local group, and our motion is shaped by the gravitational pull of nearby structures, the Virgo cluster, the Great Attractor, and other masses hidden in the distance. But for tonight, we return our focus to the local group, the small collection of galaxies that includes our own, and the neighborhood where we live, because this is the region we can study in the greatest detail. The local group is not rich or dense by cosmic standards. It is a modest collection of galaxies, but it is ours, and understanding it helps us understand how galaxies interact, merge, and evolve over time. Each galaxy in the local group has its own story, its own history of star formation, mergers, and interactions. And together they form a complete picture of how small structures grow into larger ones. The Milky Way is the product of countless mergers, and it will continue to grow by consuming its satellites and eventually by merging with Andromeda, a process that has been happening since galaxies first formed in the early universe. Measuring the Milky Way has been one of astronomy's greatest challenges because we live inside it and we cannot step outside to see its full structure, so every measurement requires indirect methods and careful reasoning. The first step in measuring the galaxy is determining distances, and astronomers have developed a distance ladder, a series of techniques that build on each other, starting with nearby objects and extending to the farthest reaches of the observable universe. For nearby stars, parallax is the most direct method, measuring the apparent shift in a star's position as Earth orbits the Sun, and from that shift, calculating the distance using simple geometry. Parallax works well for stars within a few hundred light-years, but beyond that, the shifts become too small to measure accurately, and astronomers must use other methods, each one calibrated using objects whose distances are known from the previous step. Cepheid variables are crucial for the next step because their pulsation period is directly related to their intrinsic brightness, and by measuring the period, astronomers can calculate how bright the star truly is, then compare that to how bright it appears to determine its distance. Cepheids can be seen out to tens of millions of light-years, making them useful for measuring distances to nearby galaxies, and they were the key to discovering that spiral nebulae were actually distant galaxies in the 1920s. RR Lyrae variables serve a similar purpose, but they are fainter and less luminous than Cepheids, making them useful for measuring distances within the Milky Way, particularly to globular clusters in the halo. By using RR Lyrae stars, Harlow Shapley measured the distances to globular clusters, and he realized they were distributed in a spherical halo centered far from the Sun, proving that we were not at the center of the galaxy. For more distant galaxies, astronomers use Type Ia supernovae, which have a consistent peak brightness, making them standard candles visible across billions of light-years, and they played a key role in discovering that the universe's expansion is accelerating. The distance ladder is essential for understanding the scale of the universe, but each step introduces uncertainties, and those uncertainties accumulate as you climb the ladder, so measuring distances accurately remains a major challenge in astronomy. The Gaia spacecraft has revolutionized distance measurements within the Milky Way by measuring the parallax of more than 1 billion stars with unprecedented precision, creating the most detailed three-dimensional map of the galaxy ever made. Gaia's data have refined our understanding of the galaxy's structure, revealing the shape of the spiral arms, the size of the central bar, and the distribution of stars above and below the disk, answering questions that had puzzled astronomers for decades. Mapping the galaxy also requires measuring the motions of stars, their velocities toward or away from us, measured using the Doppler shift of spectral lines, and their motions across the sky, called proper motions, measured by tracking position changes over years. By combining positions, distances, and velocities, astronomers can reconstruct the three-dimensional motions of stars, revealing how they orbit the galaxy, how they move through spiral arms, and how they interact with other structures. These motions reveal the galaxy's rotation, showing that the disk spins with stars moving faster near the center and slower near the edges, a pattern that betrays the presence of dark matter in the halo. Without dark matter, the rotation curve would drop off steeply, following Kepler's laws, but instead it remains flat or even rises slightly at large distances, indicating there is more mass than we can see, distributed in a spherical halo. The total mass of the Milky Way is difficult to measure because much of it is dark matter, but current estimates place it at about 1 trillion solar masses, including stars, gas, and dark matter combined. The visible matter, stars and gas, accounts for only about 10 to 20% of the total, and the rest is dark matter, holding the galaxy together with its gravity but remaining invisible to telescopes. Measuring the mass requires tracking the motions of objects in the halo, such as globular clusters, satellite galaxies, and stellar streams, and using their velocities to infer the gravitational pull, which reveals the total mass needed to keep them bound. Different methods give slightly different results, and the uncertainty is still fairly large. But astronomers agree that the Milky Way is a massive galaxy comparable to Andromeda, and larger than most spiral galaxies in the universe. The size of the Milky Way is also not sharply defined, because the disk gradually fades into the halo, and the halo merges with intergalactic space, so the size depends on what you measure and where you draw the boundary. The disk is about 100,000 light-years across, measured from the concentration of stars, but faint stars and gas extend beyond that, and the dark matter halo reaches much farther, perhaps 300,000 light-years or more. If you include the dark matter halo, the Milky Way overlaps with Andromeda's halo, and the two galaxies are already interacting gravitationally, even though their visible disks are still 2.5 million light-years apart. The concept of a galaxy's size is somewhat arbitrary, because galaxies do not have sharp edges, and their boundaries depend on what component you are measuring: the stars, the gas, the dark matter, or the gravitational influence. Radio telescopes have been essential for mapping the Milky Way, because radio waves pass through dust that blocks visible light, allowing astronomers to see the entire disk, including the far side beyond the galactic center. Hydrogen gas emits radio waves at a wavelength of 21 centimeters, and by mapping this emission, astronomers can trace the distribution of gas throughout the disk, revealing the spiral arms, the bar, and the overall structure. Radio observations also reveal the galaxy's rotation, because the Doppler shift of the 21 centimeter line shows whether gas is moving toward or away from us, and this information can be used to map the velocity field across the entire disk. These maps have been crucial for understanding the Milky Way's structure, and they complement optical and infrared observations which show stars and dust but are blocked by the intervening material in the disk. Infrared telescopes see through dust more easily than visible light telescopes because infrared light has longer wavelengths that scatter less, and they reveal the inner galaxy, the bulge, and the bar with greater clarity. Surveys like the 2-micron all-sky survey, or 2MASS, have mapped the entire sky in the near-infrared, revealing millions of stars in the bulge and disk, and providing data that helped confirm the existence of the central bar. The Spitzer Space Telescope and other infrared missions have studied the galaxy in even longer wavelengths, revealing warm dust, star-forming regions, and the structure of the spiral arms, complementing the data from radio and optical surveys. Together, these multi-wavelength observations paint a complete picture, showing the galaxy in different lights, each one revealing structures hidden from other wavelengths, and each one contributing to our understanding of the Milky Way's full complexity. X-ray telescopes observe the hottest and most energetic phenomena, such as supernova remnants, black holes accreting matter, and hot gas in the halo, and they reveal a side of the galaxy invisible to optical telescopes. The galactic center glows brightly in X-rays. With emission from hot gas, energetic particles, and the region around Sagittarius A star, and X-ray observations have been crucial for studying the black hole and its environment. Gamma-ray telescopes observe the highest energy photons, produced by cosmic rays interacting with gas, by pulsars, and by exotic processes near black holes, and they reveal a universe of violent and energetic events. The Fermi Gamma Ray Space Telescope has mapped the entire sky in gamma rays, revealing structures like the Fermi bubbles, giant lobes of hot gas extending above and below the galactic center, evidence of past activity from the supermassive black hole. Every wavelength reveals something new, and together they provide a complete picture of the Milky Way, from the coolest dust to the hottest gas, from the faintest red dwarfs to the brightest supernovae, and from the visible stars to the invisible dark matter. Measuring the galaxy is an ongoing process, with new surveys, new telescopes, and new techniques continually refining our understanding, and each new piece of data adds to the picture, filling in gaps and answering questions. The Milky Way is one of the best-studied galaxies in the universe because we live inside it and can observe individual stars. But paradoxically, it is also one of the hardest to study because we cannot see its full structure from our embedded position. Yet astronomers have made remarkable progress, piecing together the galaxy's shape, size, mass, and history from thousands of observations. And the picture that emerges is one of a majestic spiral, dynamic and evolving, and our home for billions of years. The Milky Way is not a static collection of stars. It is a dynamic ecosystem where matter cycles through different phases, from gas to stars and back to gas, enriching the galaxy with heavy elements and sustaining star formation over billions of years. This cycle begins with the interstellar medium, the gas and dust that fills the space between stars, and it provides the raw material for new star formation, the canvas on which the galaxy writes its story. The interstellar medium is mostly hydrogen, about 70% by mass, with helium making up most of the rest, and trace amounts of heavier elements like carbon, nitrogen, oxygen, and iron, all forged in stars and scattered into space. The gas exists in different phases: cold molecular clouds, cool atomic gas, warm ionized gas, and hot tenuous gas, each one with different temperatures, densities, and physical properties, and each one playing a role in the galactic ecosystem. Molecular clouds are the coldest and densest phase, with temperatures around 10 to 20 degrees above absolute zero, and they are the sites of star formation, where gravity can overcome internal pressure and pull the gas into collapsing cores that become stars. These clouds are traced by molecules like carbon monoxide, which emits radio waves that telescopes can detect, and by mapping the emission, astronomers can see where molecular clouds are located and estimate their masses. The clouds are patchy and clumped, not smooth, with dense cores embedded in more diffuse envelopes, and they are supported against collapse by turbulence, magnetic fields, and the pressure from the random motions of molecules. When a cloud is compressed by a spiral density wave, a supernova shock wave, or a collision with another cloud, it can begin to collapse, fragmenting into smaller clumps that each form a star or a cluster of stars. Once stars form, they begin to affect their surroundings, emitting light, wind, and eventually, for massive stars, dying in supernova explosions that scatter enriched gas back into the interstellar medium. Young massive stars emit intense ultraviolet radiation, which ionizes the surrounding gas, creating glowing HII regions, and their stellar winds blow bubbles in the gas, sweeping material away and compressing it into dense shells. These processes trigger new star formation because the compressed shells can become unstable and collapse, forming a new generation of stars, and this feedback loop can sustain star formation for millions of years in a single molecular cloud. Eventually, the cloud is dispersed, the gas blown away or consumed by star formation, and the remaining stars drift apart, forming loose, open clusters that gradually dissolve as the stars move on independent orbits. Supernova explosions are the most dramatic form of stellar feedback, releasing enormous amounts of energy and scattering heavy elements into space, and they play a crucial role in enriching the interstellar medium and regulating star formation. When a massive star explodes, it ejects its outer layers at speeds of thousands of kilometers per second, creating a blast wave that sweeps through the surrounding gas, heating it and compressing it into expanding shells. The shell continues to expand for thousands or millions of years, gradually slowing as it plows into more gas. And eventually it merges with the general interstellar medium, mixing the enriched material with the existing gas. The heavy elements created in the star's core and in the explosion itself are now available for incorporation into new stars, and over billions of years, this process has increased the metallicity of the galaxy from nearly zero to the few percent we see today. Stellar winds from massive stars also contribute, carrying away mass throughout the star's life and enriching the surrounding gas. And for the most massive stars, the wind can remove more mass than the supernova explosion itself. Lower mass stars like the Sun also return material to the interstellar medium, though more gently, by shedding their outer layers at the end of their lives, forming planetary nebulae that glow with the light of the exposed stellar core. Planetary nebulae are beautiful, glowing shells of gas, expanding slowly away from the dying star, and they enrich the medium with carbon and nitrogen produced in the star's interior through nuclear reactions. White dwarfs, the remnants left behind, slowly cool over billions of years, contributing nothing more to the ecosystem, but the gas they expelled continues to mix and cycle through the galaxy. The interstellar medium is not uniform. It is stirred and mixed by stellar feedback, supernova explosions, and the rotation of the galaxy, creating a turbulent, dynamic environment where gas clouds collide, merge, and fragment. Turbulence is driven by energy input from stars, and it prevents the gas from collapsing uniformly, instead creating a complex structure of filaments, clumps, and voids, and this structure affects where and when stars can form. Magnetic fields thread through the gas, shaped by turbulence and rotation, and they provide additional support against collapse, particularly in diffuse regions where the gas density is low and gravity is weak. The fields also affect the motions of charged particles, cosmic rays, which are accelerated by supernova shocks and other processes, and these particles heat the gas and provide pressure that helps resist gravitational collapse. Cosmic rays are high-energy particles, mostly protons, that travel through the galaxy at nearly the speed of light, and they interact with gas, producing gamma rays and other radiation that telescopes can detect. These particles are important for the energy budget of the interstellar medium because they carry a significant amount of energy comparable to the energy in starlight or in magnetic fields, and they help regulate the temperature and ionization state of the gas. Cosmic rays also play a role in star formation by ionizing gas deep inside molecular clouds where starlight cannot penetrate. And this ionization allows magnetic fields to couple to the gas, affecting how clouds collapse. The origin of cosmic rays is still being studied, but supernova remnants are thought to be the main source, accelerating particles through shocks as the blast wave expands, and some of the highest energy cosmic rays may come from more exotic sources like black holes or pulsars. The cycle of matter through the galaxy is slow, taking hundreds of millions of years for gas to condense into stars, for stars to live and die, and for the enriched gas to be incorporated into new stars. But over billions of years, this cycle has transformed the galaxy, gradually increasing the metallicity of the gas, changing the types of stars that form, and creating the chemical diversity that makes planets and life possible. Early in the galaxy's history, the gas was almost pure hydrogen and helium, and the first stars that formed contained no heavy elements, making them very different from the Sun and other stars we see today. These first stars, called population 3 stars, were likely very massive, burning hot and bright, and dying quickly in supernova explosions that scattered the first heavy elements into space, seeding the next generation of stars. No population 3 stars have ever been observed, because they all died billions of years ago, but their influence is seen in the chemistry of the oldest stars, which contain tiny amounts of heavy elements from those first supernovae. By studying these ancient stars, astronomers can learn about the first generation of stars, what they were like, how massive they were, and how they enriched the early universe with heavy elements. The Milky Way has been recycling material for 13 billion years, and the Sun and Earth are products of that recycling, made from gas that has cycled through multiple generations of stars, each one adding new elements to the mix. The iron in your blood, the calcium in your bones, the oxygen you breathe, all of these elements were forged in stars and scattered into space by supernovae, making us quite literally stardust, children of the galactic ecosystem. When you look up at the night sky, you are seeing the galaxy from within, the band of the Milky Way stretching across the darkness, a reminder that we live inside a vast structure and that our view is limited by our position but enriched by our ability to understand it. The stars you see are your neighbors, members of the same spiral arm, drifting through space alongside the Sun, and each one is a sun, potentially with planets, moons, and perhaps even life of its own. The light from those stars has traveled for years, decades, or even centuries to reach your eyes, So when you look at the sky, you are seeing the past, a mosaic of light from different times and distances, all arriving together tonight. Some of those stars may already be dead, their light still traveling toward us, and others are just being born, hidden in clouds of dust, their light not yet visible but already shaping the galaxy's future. The Milky Way is not eternal. It has a history and a future. It formed billions of years ago from smaller structures, and it will continue to evolve, merging with Andromeda, consuming its satellites, and eventually becoming part of a larger galaxy in the distant future. But for now, it is stable, rotating steadily, and it will remain recognizable for billions of years, long enough for countless generations of stars to be born and die, and long enough for life to evolve, spread, and perhaps one day leave the planet to explore the galaxy itself. Our perspective is unique. We are the first generation to understand the Milky Way's structure, to map its spiral arms, to measure its mass, and to trace its history through the chemistry of ancient stars. Previous generations saw the Milky Way as a mystery, a band of light with no clear explanation, and it is only in the last century that we have learned the truth, that we live inside a galaxy, one among billions, and that the universe is far larger than we ever imagined. This knowledge is both humbling and empowering. Humbling because it shows how small we are in the cosmic scheme, just one planet among trillions, and empowering because it reveals that we can understand the universe, even from our tiny vantage point, using light, mathematics, and the power of human curiosity. The Milky Way is our home, and understanding it is part of understanding ourselves, our origin, our place, and our connection to the cosmos, a connection that is real and physical, not just philosophical or spiritual. Every time you look at the night sky, you are looking at home, not just Earth, not just the solar system, but the entire galaxy, the vast structure that holds us all, and that has existed long before we were here and will continue long after we are gone. The galaxy does not care about us. It does not know we exist, but we care about it, because it is beautiful, because it is knowable, and because understanding it gives meaning to our existence, a sense of place in the universe. So as you drift towards sleep, let your mind wander through the galaxy, imagining the spiral arms, the central bar, the ancient halo, and the countless stars moving together in their long, slow orbits. Picture the sun carrying Earth through space, passing through spiral arms, bobbing up and down through the disk, and completing its endless journey around the galactic center, a journey that began long before life appeared on Earth and will continue long after. Imagine the dark matter halo surrounding everything, invisible but essential, holding the galaxy together with its gravity, a mysterious presence that shapes the structure of the cosmos but remains hidden from our eyes. And think of the satellites orbiting around us, the Magellanic Clouds, the dwarf galaxies, and the streams of stars from consumed neighbors, all of them part of the Milky Way's extended family bound together by gravity. Star formation in the Milky Way continues today, at a rate of about 1 to 2 solar masses per year, but this rate has declined over time, as the gas supply has been gradually depleted by star formation and by gas being ejected from the galaxy by supernova-driven winds. In the early universe, galaxies like the Milky Way formed stars much more rapidly, perhaps 10 or even 100 times faster than today, and the sky would have been much brighter, filled with massive blue stars and frequent supernova explosions. As the gas was consumed, the star formation rate declined, and the galaxy settled into a more quiescent state, with ongoing but slower star formation, and this transition has shaped the stellar population we see today. In the future, star formation will continue to decline, as the remaining gas is used up, and eventually the Milky Way will become a red and dead galaxy, dominated by old stars with little ongoing star formation, unless it merges with another gas-rich galaxy and reignites the process. The merger with Andromeda will likely trigger a burst of star formation, as the gas from both galaxies collides and compresses, forming massive new stars and lighting up the combined galaxy with blue clusters and glowing nebula. But that burst will be temporary, and once the gas is depleted, star formation will cease, leaving behind an elliptical galaxy filled with old red and yellow stars, slowly fading over trillions of years. For now, the Milky Way remains active. New stars continue to form, and the galactic ecosystem continues to cycle matter through its various phases, sustaining the beauty and complexity of the galaxy we call home. This cycle is essential for life, because without it, there would be no heavy elements, no planets, no water, and no possibility for biology, making the galactic ecosystem not just beautiful, but necessary for our existence. We have travelled across the Milky Way, from our position in the Orion arm outward to the halo, inward to the centre, and through the spiral arms where new stars are born, and now we return home to Earth, to our place in this vast structure. The Milky Way is our galaxy, the collection of hundreds of billions of stars that surrounds us, and we are part of it. Not separate observers, but embedded citizens, made from its material and carried along by its motion. Every atom in your body was forged in a star. Carbon, oxygen, nitrogen, iron, all of them created in nuclear reactions deep within stellar cores and scattered into space when those stars died, eventually condensing into the gas cloud that formed the sun and planets. You are stardust, quite literally. And your connection to the galaxy is not just poetic, it is physical, a direct lineage from ancient stars to the present moment, linking you to the cosmic history of matter and energy. The Milky Way is patient. It moves on timescales we can barely comprehend, its galactic years measured in hundreds of millions of Earth years, and its history written in the motions and chemistry of stars that have been shining for billions of years. We are brief visitors, living for decades in a structure that has existed for eons, but our brief moment is enough to learn, to understand, and to appreciate the galaxy that gave us life. There is something comforting in that, the knowledge that we are part of something larger, something ancient, something beautiful, and that our existence, however brief, is woven into the story of the galaxy. So rest now, knowing that the Milky Way is still turning, the stars are still shining, and the universe continues its slow evolution, indifferent to us but magnificent in its structure, and we are fortunate to be here to witness it. The spiral arms will keep glowing with young stars, nebulae will continue to form and disperse, and supernovae will scatter heavy elements into space, enriching the gas for future generations of stars and planets. The galactic center will remain hidden behind dust. Sagittarius A star will continue its quiet vigil, occasionally flaring when gas falls inward, and the bar will rotate steadily, shaping the flow of matter through the inner galaxy. The halo will preserve its ancient stars, globular clusters orbiting slowly, and stellar streams marking the deaths of small galaxies, a fossil record of the Milky Way's growth written in the positions of stars. And the satellites will continue their dance, the Magellanic Clouds moving through the halo, dwarf galaxies orbiting in the dark, and all of them slowly being pulled closer, destined eventually to merge with the Milky Way and add their stars to ours. Billions of years from now, Andromeda will loom large in the sky, its spiral arms visible to the naked eye, and the two galaxies will collide, a slow cosmic embrace that will reshape both and create something entirely new. But that is far in the future. And for now, the Milky Way is our home, stable and beautiful, a spiral galaxy spinning quietly through space, and we are here, alive, aware, and able to understand it. That understanding is a gift, the product of centuries of observation, thought, and discovery, and it connects us to every astronomer who ever looked up and wondered about the stars, and to every person who will come after us, continuing the journey of learning. The Milky Way is not just where we live, it is who we are, our history written in starlight, our future unfolding in the slow dance of gravity, and our existence made possible by the cycles of matter through the galactic ecosystem. So when you look at the Milky Way tonight, remember that you are seeing home, not as a place, but as a process, a vast structure billions of years old, slowly evolving. And we are part of it, temporary but real, brief but connected to everything that came before and everything that will come after. Rest easy, knowing the galaxy will continue, the stars will keep shining, new worlds will form, and the Milky Way will turn through space, carrying us all on its long journey through time. And perhaps someday, far in the future, our descendants will leave Earth, traveling to other stars, exploring the galaxy we have studied from afar, and seeing firsthand the wonders we have only imagined tonight. But for now, this moment is enough. The knowledge, the wonder, the quiet appreciation of our place in the cosmos, and the simple beauty of knowing we are home in the Milky Way. Sleep well, knowing the universe is vast, the galaxy is ancient, and you are exactly where you need to be, a small part of something magnificent, carried along by the slow turning of stars. Thank you for journeying with me tonight, through the spiral arms, past the center, out to the halo, and back home again. And I hope you found something beautiful, something calming, or simply a moment of peace. The Milky Way will be here tomorrow, and the night after, and for billions of nights to come, and you can return to it whenever you need, in the sky above, or in the quiet space of your imagination. Until next time, rest well, let the stars watch over you, and remember that you are made of stardust, a child of the galaxy, connected to everything that shines in the darkness above. Good night, and may your dreams carry you through the turning spiral, where time moves slowly, distances are vast, and the universe holds infinite wonders waiting to be discovered.